Hi fellas, this is Chemaddicts again to the solution. Welcome back to my another video tutorial. Now what we are gonna do is uh, we're gonna interpret this data given in a graph, okay? And we're gonna find the find some of the essential values from this analysis, okay? So let's get started. So let's study the question. The question says the rate constant for the reaction between bromoethene and hydroxide ions was determined at five different temperatures. The results are shown in the table below. Okay, so these are the things that are given here. So here temperature is given, reciprocal of temperature, then rate constant K, ln K. Okay, so at first they have asked us to complete the missing values in the table. Okay, so as you can see that uh, in here this is 1 by T, that is reciprocal of this temperature. So let us just reciprocal this temperature. 1 by 133 will give us, sorry, 1 by 333 will give us 3.00 into 10 to the power minus 3. Okay, why do I write always this as 5, 3 as 5? That's my problem, a real good issue. Okay, yeah, 3 into 10 to the power minus 3. So that's the value. Then let us find this. This is simply ln k, that is log to the base e k. Log to the base e k is ln k. Okay. I hope that you have understood. So just substituting the value of ln k in here, this the value for ln k is 377 into 10 to the power minus 3. 3.77 3.77 into 10 to the power minus 3, which will give us as minus 5.8, that minus 5.58. So why we are finding the value for 1 by T and ln k? Why? What is the reason behind for finding the value for this and this? Well, uh, the answer will come from this question from part 2. So I hope that you have understood how to complete the missing values. It's really simple. Okay, so now let us study why we need to find the value for 1 by T and ln k. Okay, well, uh, the answer is in this question. We will find the answer in this question. So plot a graph of ln k against 1 by T. Calculate the gradient of your graph and use this to calculate the activation energy. The Arrhenius equation can be expressed as this. Well, fine, this is the Arrhenius equation. Now we have came to know that this is the Arrhenius equation. Arrhenius, well, whatever, Arrhenius equation. Okay, so this is what? Oh, fine. So here we can see that we have ln k, then we have 1 by T. So that's why, oh, that's why we have found the value for ln k and 1 by T. So that is why we have found these values. Well, there is another reason for finding ln k. Okay, since the rate constant, the value for rate constant is really slow. The value for rate constant is really slow. Sorry, not slow, small. Why am I speaking the wrong things? This is small. The value for rate constant is really small, not slow. The reaction might be fast or slow, but the rate is the value for this rate constant is really small. Okay, so to make the values bigger, so we have introduced ln k, just like Apple, iPhone. So we have introduced the new feature ln k. So it would be the people might find it easier to deal with these values. Okay, our new iPhone what 10, ha ha ha. So this is the new feature that we can make the values bigger. Here the if we just if we just introduce ln k, then we can see that the smaller values become bigger. Here this small value drastically changes to bigger value, as you can see, as you can compare, as we can compare, sorry, we can compare. Okay, as we can compare. So that is how it's done. Okay, so now let us study this question. In this question, they have asked us to plot a graph of ln k against 1 by t. Calculate the gradient of your graph and use this to calculate the activation energy. The Arrhenius equation can be expressed as this. Well, fellas, now let us plot this graph. Okay. Well, it should be here somewhere. Yeah. So, fellas, as you can see, I have borrowed a student's graph paper. Okay, I'm really sorry for that. That my graph plotting is really bad, but still, as you can see, let us study this student's plotting. Okay, so let us find some of the mistakes that the student has made. Okay, so uh, here let us at first let us examine these values over here. So in here the scaling is correct. Okay, for scaling the student has achieved the mark. Okay, scaling is correct. The scaling is definitely correct. Yeah. See, the scaling is definitely correct. So here the length, as you can see, is proportional. The lengths are same, equal, accurately equal. As long as the length is equal, then the examiner will give you the marks for scaling. Okay, this is for this axis, and this also goes with the other axis. Okay, other y-axis. Here the scaling is the main factor. Okay, here the lengths are equal. Okay, so as you can see that the scaling is equal. No, the scaling is maintained over here. Sorry, the scaling is maintained. They are not equal. The scaling in x axis is not equal to the scaling in y axis. They are not equal, but the scaling is maintained. So you should at least maintain the scaling. Okay, we should at least maintain the scaling. Okay, then we can easily take the values, as it's up to us how do we need to scale. Okay, so in here the student has taken these values as follows. Okay, on the x-axis, and on the y-axis the student has taken uh, 10 boxes 1 unit, as you can see. Okay, so that goes with scaling. Okay, scaling is also correct in y-axis. Scaling, sorry, scaling is also correct in y-axis. This is y-axis, as you all know, no need to say. And scaling is also correct in x-axis. Okay, fine, excellent. So now the second mark uh, would go for plotting. So here you need to plot very accurately according to the scale. Okay, So in here, what should we say that, so 1 unit cost 10 boxes. Okay, 10 boxes is 1 unit, 10 boxes is 1 unit. So one box should have 1 by 10, that is 0.1 on y-axis. Okay, 0.1 on a y-axis, y-axis, on y-axis. That's fine. That's totally fine. On x-axis, let us find the smallest division. This should be useful in later calculation on this plotting. This is useful for plotting. Okay. So on x-axis, let us find. Uh, let's see. Well, let us now see the data for this reciprocal for 1 by t. Then we can understand. So as you can see, okay, we can see that the these values 10 to the power minus 3 is constant for everything. So we can ignore this thing. Okay, we can ignore this 10 to the power minus 3 in total. Okay, so now we have the values just like 3.41, 3.30, 3.19, 3.10, 3.00. So as in here we can see that it is roughly 0.1 difference in here. Okay, so let's see how we have carried out the scaling. Yep. Okay, let's see the scaling. Well, so in here 20, so point 1 is since everything is in 10 to the power minus 3, so we are ignoring that 10 to the power minus 3 thing. Okay, so we are dealing with 3.1. This is 3.1. So on x-axis, let's see. I'm just making your plotting easier. Okay, don't need to worry. So 10 boxes represents 0.1 unit. Okay, suppose we are just ignoring this thing, this weird thing. Okay, since it is constant throughout the calculation, since 10 to the power minus 3 is constant, so we are ignoring that for a while. Okay, so for 1 unit you will get 0.1 by 10, which is what, 0.01. Well, so one box represents 0.01. Okay, so we have got it.